Yeah. Feeling good? Feeling good? Yeah.
What are you working on? Like functional work? Which team?
I'm maintaining Drizzle Pack, but I'm moving over to James Webb soon. And I'm very excited.
James Webb for what?
I'm not sure.
Ah,
Yeah, I don't
okay.
know.
Good.
Yeah. I need to find Jake. I forgot to do that.
Hello, hello.
Okay, good morning, everyone. Welcome to day 4 of Inter+Stellar. We have an awesome invited talk this morning by Lindsay. And Yumi, if you want to introduce yourself, you're chairing the session this morning.
I'm Yumi Choi. I'm chairing this session, the morning sessions. Yeah, welcome everyone. We've got great talks lined up today as well. So our first speaker is Kara. We'll be talking about the hungry Milky Way.
Hi, thank you. All right, is this microphone working okay? Yes? Awesome. Title chosen before time slot. I feel like you're probably not hungry yet, but I was like, maybe right before lunch. So I'm going to be talking today all about when will lunch be served for the supermassive black hole at the center of our galaxy. And I studied the central molecular zone, and that's really the region that is controlling how much gas comes from the outside of the galaxy, and then how much is going to flow inwards into the very center of the galaxy, and also a place where really cool star formation happens. And I'm going to show lots of fun movies. Okay, so really just looking at gas flows in our galaxy center. This is an external galaxy, obviously. There's like no amount of money that I wouldn't pay to like get this image of our own galaxy, right? How much is that going to cost, Josh? All right. Yeah, but so we do simulations to try to get our best, perspective of that as well. So I missed a couple of talks this week already, so I'm sorry for the talks that I missed. It looks like there were some really good ones. I have 2 little tiny kids, and so this is my balance of like being gone for 2 days instead of a whole week, but still getting to do conferences. So I hope you all understand and appreciate and feel empowered to make that kind of choice for yourself too, if that's a good choice for you. If you didn't know UConn had an astrophysics program, now you do. We're great. Come visit us. It's a pretty big group. The Milky Way Lab is my research group. I don't know how we got to be so large, but there we are. And they're the ones who are responsible for all the work that I'm going to show today. So I'll try to show pictures as we go, but they are the cool ones. All right, so galaxy centers are varied. You probably know this already, but they're varied in terms of their size, the shapes of the galaxy center. So most galaxies have what's called the central molecular zone around them. So somewhere between 100 parsecs to a couple hundred parsecs to a kiloparsec around the central supermassive black hole. There's usually this inner region of molecular gas that can form a ring or spiral arms or some kind of weird like spirally thing that's sort of ring-like. And that is the central molecular zone. And galaxies also have very different properties in their centers in terms of like star formation. So this is NGC 253, which is a starburst at the center. And this is obviously a radio lobe from Vela and Hubble, which shows a very active galactic nucleus where that central supermassive black hole is feeding and having huge amounts of feedback. So this central region is really something that helps control galaxy evolution because AGN feedback is so disruptive and can really affect an entire galaxy in such a big way. We really want to understand, or like, I guess I really want to understand why does sometimes the gas go into the nuclear cluster and why does it sometimes not go into the nuclear cluster? So we're going to look at all the pieces of this diagram. So the gas that flows in to the inner central molecular zone, CMZ, from the outside of the disk of the galaxy. Some of that gas just continues to orbit for potentially a long period of time. Some of it forms stars. Some of it then outflows again, and some of that flows into the nuclear cluster. And then, of course, you can have outflows there as well. Currently, our galactic center is quiescent at the moment. I'm OK with that. Yeah, I don't know what it would look like. So I feel like some people think that makes it like not interesting to study in terms of like AGN, but like there's probably gas that's going to enter it someday. There probably is gas that has gone in to the center at some point in the past. So it's just like a snapshot of galaxy evolution that we can study and that we can understand. And so this is what it looks like from a side view perspective. So nice galaxy. We're just looking through all the stuff along the side. And so Sagittarius A star would be this supermassive black hole at the center. And this whole kind of clump of gas and dust, that's our central molecular zone. And this central molecular zone is actually very distinct from the rest of the galaxy. So again, this is not a picture of our galaxy. I'm just using it as an example of what a barred spiral galaxy kind of looks like. So in this case, you have, this would be like that central molecular zone. And these are dust lanes feeding in to the central region here. And it's like a separate part physically from the rest of the galaxy, right? There's a physical separation between that central molecular zone and other parts of the galaxy that's just connected by these dust lanes, which mostly only flow in, not out. And this is from a paper earlier this year, where basically if you just look at the mass per unit longitude over the inner 40 degrees of the galaxy, you can see a big spike in the center there, and that big continuous spike of much higher density gas than the rest of the galaxy, all in one place. That's what we call the central molecular zone. So it's very separate, and it also has very different physical properties. So compared with gas in the galactic disk, you're talking about densities of about 1 or 2 orders of magnitude higher on average. More chemical complexity, much higher magnetic fields, about milligauss strength. The dense gas is very hot, so normally in like a molecular cloud in the galactic disk, you're looking at like maybe 20, 25 Kelvin. In the galactic center, you're looking at least 50 Kelvin, if not hundreds of Kelvin for the dense gas. And the gas is also highly turbulent. This is a really small plot, but it's just showing the size versus the line width for a local molecular cloud, Perseus here, versus galactic center molecular clouds. This is from Shetty 2020. Newer studies have shown this as well, is that the galactic center just falls in a different place on the size line width relationship. So very much more turbulent. So a separate area from the rest of our galaxy. So as you can probably guess though, the star formation activity of our galaxy, as well as its AGN activity, has probably varied over time. And so we want to understand how these gas flows work, what they might have been like in the past, and what they might be like in the future. So let's go through each one of these. I'm just going to simplify this beautiful figure from Betsy Mills into 4 categories. So gas inflow from the disk. So that's, let me just show these simulations again quickly. So this is a simulation from Matthias Romani and Robin Truss. And so here is like the 1 kiloparsec scale bar here, where you're seeing the larger disk of the galaxy. These are the dust lanes where gas is flowing in from the disk of the galaxy into the center. Basically, as the bar rotates, the ends of the bar have some kind of friction with the gas that it encounters. That friction means that some of the gas loses some energy, loses some angular momentum, and starts to fall inwards along the bar. That's what those dust lanes are. They're falling inwards along the bar, and then they just come to this point here where there's these semi-stable orbits called X2 orbits, which are pseudo-elliptical, and then that's what the zoom-in panel is here. But you can see, like, if you just imagine pausing this at any moment in time and taking a snapshot and being like, what is the 3D structure of that? You'd be like, ooh, kind of messy, kind of confusing, there's kind of a lot. So think of that again later when I start to show you our results. Okay. Okay, so here are the 4 different types of like gas flows that we're going to look at. I think if you could solve all of these, you could sort of solve the equation of like where the gas is going, how much, at what speed, etc. So the gas outflow I'm not going to talk about very much today. If you're interested, you should read about the Fermi bubbles and the galactic center bubbles. And you should study the diffuse ISM above and below the galactic plane. There's not like a fixed answer to this, and it's not something that I have anything useful to contribute to. So read about that stuff if you want. The gas inflow to the CMZ, I can say something about this. So a former graduate student, H. Perry Hatchfield, he ran some simulations, and he put in tracer particles. And so he basically was able to calculate if you put tracer particles in one of these simulations along the dust bar, the dust lane along the bar, how much of that then gets accreted onto the CMZ. And what he found is that the material usually overshoots 1 to 3 times on average is how many times it overshoots. So some of it goes in, it goes around again. Some of it falls in the next time, it goes around again. Some of it falls in again the next time. What's useful about that is that then you can actually take real data, so position velocity diagrams of like how the gas is moving in the center, compare that with what these dust lanes look like in the simulations and say, ah, this part of the PV diagram, a very specific part of it, that is the part that is falling into the center of the galaxy. I can measure the mass of that from CO, and then I can measure the speed at which it's falling in by deconstructing from the face-on view to the top-down view, which you get from the simulations. And then we know that it overshoots, and so you can say, well, it doesn't usually happen right away. It takes a little bit longer, so you get an updated mass inflow rate. And so he found a mass inflow rate of about 0.8 solar masses per year with a nice hefty error bar for fun. I'll talk a little bit longer about the star formation, because this is a lot of what I work on. So a lot of the gas that gets on these orbits, these X2 orbits around the center here, they can orbit for a long time, but a lot of them go on to form stars. So there's a much higher density of stars in the center of the galaxy than anywhere else in the galaxy. I think you all probably know that already, but it's a crazy high density of stars. Like if you could see the night sky from the galactic center, it would be awesome and maybe dangerous because of all like supernova going off, all that stuff. But it would be awesome. So the key takeaways, which I'll go through one by one, is that the current star formation rate in the center is lower than expected given the amount of dense gas. You may have heard this before at other talks. I no longer think that's a problem for two reasons. One, because individual molecular clouds follow this star formation relationship, so those are totally fine. And also, there's really good reason to think that star formation rates in galactic centers may not be a flat, constant, never-changing perfect value, but they probably fluctuate, right? It's a highly dynamic system. Instead of having the slow spinning of the galaxy be the only real dynamical forces at work, you have really fast dynamical times, especially compared with the star formation timescale. So the dynamical time and the star formation timescale are about the same order. And so dynamical changes to the system, like new mass being accreted, will affect the star formation rate. And we have a new ALMA large program that's going to help us to answer some of this. So here's the plot that shows that the current star formation rate in the CMZ is lower than expected. So you have star formation rate as a function of dense gas. Notably, if you looked at just regular gas, you don't see anything weird about the CMZ. It's really if you're just like, stars must form in dense gas, which I think all of us agree on. The CMZ just has a ton of dense gas, okay? So if you look at the amount of dense gas that it has compared to the star formation rate, it actually falls significantly below the trend marked here, for example, the LADA 2012 relationship, but also falls lower than like Milky Way clouds, for example, or other disk galaxies, other extragalactic CMZs or high redshift galaxies. Now that's the whole CMZ overall. We did like a super fun dendrogram hierarchical catalog of all the structures in the CMZ, and where we could like categorize all their properties and kinematics and whatever numbers you could ever want are there. And for star formation rates, we found that the individual CMZ clouds, they do follow this relationship. It's just really the overall CMZ that is lower. So the molecular clouds in general follow this. It's just there's a lot of dense gas that's not engaged in star formation. And so a lot of the gas is probably just too turbulent to engage in the star formation process. But once it starts the star formation process, it seems to proceed as normal. There's also some good theory that suggests that star formation in galaxy centers may be episodic. So we have one analytic theory paper and then also two simulation papers that all show that, again, because it's a highly dynamic system, you might expect that it's harder for the gas to form stars because it's so turbulent. Once it forms stars, it has a huge burst of star formation, blows out all the gas and dust. It just goes away. Takes a while for that inflow to replenish that material. Once it replenishes that material, it continues to build up until it reaches the threshold for star formation, has a big burst again. And so that is one thing that people are actively investigating, because the theory suggests that this is a good explanation. It's also a good explanation for like why our star formation rate is relatively low in the galactic center. My student Perry, he also found some indication that the present day star formation rate may be higher I'd say it's pretty tentative, but something worth investigating further. We're currently doing a new ALMA large program called ACES, the ALMA CMZ Exploration Survey. You gotta love like the double encoded acronyms on acronyms on acronyms. Yep. It's a fun team. It's a huge collaboration. I'm showing just a fraction of the pictures, but we're doing a 3mm survey of the entire CMZ at 2 arcsecond resolution, dust continuum, and spectral lines. Here's some pretty data. Ooh. Oh, you can make a 3D cube with position, velocity. What? Ooh. I'll show you the real science when we finish our papers, but for now, pretty pictures. My awesome student, Jen Wallace, is working on making a core catalog for all of these. So she's identifying and classifying the compact sources in the CMZ, determining their physical properties and their star formation potential. She's comparing with the galactic disk to say, how is it similar, how is it different in this environment? And she's going to help us better understand how cloud environment can impact star formation. These cores are really complicated because it's a 3mm survey, so some of these things are like probably protostellar cores, and some of them are probably like filaments of like synchrotron emission or ionized gas or magnetic field driven things. And so she's doing like a fun Zooniverse project to help with identification. And this is like the initial catalog that she has and like the longitude and latitude distribution. Okay, that's star formation. I should have put the rate. We do have a star formation rate. It's about 0.07 solar masses per year. I'll add that next time. 0.7. 0.7. This is why I'm looking at you. No, Civic, can you? 0.07. It's like 0.1, right? Okay. It's like 0.1 is what I want to say. 0.1 solar masses per year.
Or couldn't hear you.
0.1. So it's a less number than this. I'm not going to do the math yet because we don't have all the numbers, so it would just be like confusing. But that's where we're getting to. Does that make sense? That's where we're going to. Okay. So one thing I'm super excited about now is like, how do we get this gas inflow? How do we look at how much gas may be there? And the thing that we've figured out is that you really cannot do this without knowing the 3D structure of the CMZ. If you don't know the 3D structure, you can't say anything about what gas is potentially moving into the center, how much, how quickly, what that rate is. And so we spent a really long time doing this super fun 3D CMZ project. Side view, so frustrating. This is our best guess of what it looks like from the top down. And this is, of course, based on simulations. And like, you know, the simulations are based on theory. There's a lot of good math and physics there. But I'm just going to be like, look at the picture. Look at this picture. OK. This is the time average simulation. Sorry, this is the time integrated version of the simulation that I showed you before. So it is kind of a chaotic mess, but when you do the time integrated version, you can see that there are patterns. So here is your dust lanes that are feeding the gas inwards. You can see there's a whole family of orbits as well. It's not just a simple single orbit. And then your CMZ here is kind of like elliptical-ish, like X2 orbit. So as far as we can tell, this is a pretty good model of what the top-down view looks like of the dust lanes and the central region here. But one really finicky part is the 3D structure, particularly of the CMZ itself. Here are just 3 models from the literature that we made this figure for our protostars and planets review, where we have a spiral arm model, closed elliptical orbit, and then an open stream kind of pretzel-like orbit as well. All of these fit the data as well as any others. But as you can see, they place individual clouds at different parts of the CMZ. And so basically, like by just distinguishing between whether clouds are on the near side or on the far side, you could help to distinguish between these models. And when we look at the data, so we made our big hierarchical catalog of structures, which is the starting point for our analysis. And then we started looking at using dust extinction and emission to distinguish near from far. Because when you look at the data itself, this is like your Herschel column density map. This is optically thin. It tells you the true amount of gas and dust that are present there. This is your Spitzer 8 micron data. And so this is optically thick in places where there's a cloud. And so at that location of the green square there, that's a cloud called the brick. And it is a shadow. It is completely absorbed the background radiation, and it is very dark. And so by looking at the column density map, you can say, okay, well, I know that there's a lot of stuff there, and it's an absorption, so that's more likely to be on the front side of the galactic center, whereas this cloud also has a significant amount of column density, and I don't see any absorption whatsoever. So that one is more likely to be on the far side. So I'm not going to sell my home on any one cloud, except for maybe the brick. Like, that's definitely on the front side, okay? The other ones, we just do probabilities. We do probabilities and we try to combine them all together to distinguish between these models. We also have a paper that Dan Walker wrote using spectral lines. So H2CO in the radio has this really cool feature where it absorbs really well. And because the galactic center is pretty much bright at all wavelengths, if you have a cloud in front and you have something that will absorb, it's going to absorb that gas. And so we also studied the spectral lines. And then we were able to make these plots where we assigned for each cloud which ones we were very confident were near, uncertain, likely far, or far. And then we put those 3 models there in the same color scheme. So blue is the part of the model that's on the front side. Red is the part of the model that's on the back side. So if red is with red, that's good. If blue is with blue, that's good. And you can see we have perfect fits, and everything works super simply and well, right? We also made our own ellipse model because the Molinari model doesn't obey angular momentum conservation, and we have like a new updated potential, so we just were like, there's also an ellipse model that fits the data slightly better, so to not rule out ellipses. We can also look at the longitude velocity space as well. So we have information about the velocity of the clouds. And you can see, again, perfect matches. Not perfect matches. I would say we can probably rule out these 2. Those are really not consistent in a lot of ways with the data, particularly like the LB on the top left one. And the ones that are left, the KDL and the ellipse one, are all these like elliptical-like shaped ones. So we think that some of this like elliptical like fit is a good idea for the structure of the CMZ. You can follow along with our work. So I just presented the work on 4 papers that came out this spring. And we have a website, and all our data and all our code are public. We have a little 3D viewer you can check out, so you can follow along there. But I'll also give you a sneak preview of what we're doing now. OK. So we're also adding in star counts. So this is from Nishiyama 2013, just looking at star counts compared with models of the nuclear stellar disk. And you can see, again, places where there are these clouds, they tend to be darker than the model. The brick in particular is very dark compared with the model. And so that also gives us a quantitative measurement of the likelihood that the cloud is on the near or the far side. Danny has now combined all of these into a Bayesian probability distribution calculator. So you can basically take all of the calculations that we've done, the dust extinction, dust emission, spectral line extinction, star counts, and also X-rays, which we'll talk about in a second. You can combine them into one posterior and get a likelihood curve. And then you can like fit those likelihood curves in 4 dimensions. You can fit your longitude, latitude, velocity, and near far likelihood with models, and we can fit. And so this is a preliminary plot of what we think the top-down view might look like with all the clouds and like their line of sight positions with big error bars. And then we don't think there's any way that a single X2 orbit fits, but maybe like a family of X2 orbits would be a good model. And so I think we're getting closer to this 3D model and also identifying the stuff that's falling inwards. And so once we have like a model of like where the majority of the gas is on those X2 orbits, you can also point out things that are separate from that are then falling inwards towards the center, which things aren't part of this model, which things have different velocities, which things are separate. And we're starting to do a little bit of that. OK, we also have a superpower, which is using X-ray flares. So Sagittarius A star is a supermassive black hole at the center of our galaxy. And in the past, it did give off X-ray light when it had an accretion event. That X-ray light came to Earth, saw that we didn't have an X-ray telescope, and so it kept going and is long gone. That X-ray light also went sideways and saw that there was a molecular cloud there. It fluoresces that molecular cloud and actually does like individual slices of fluorescence of that molecular cloud with time. Then that fluoresced light re-emits in all directions, some of which then goes to the Earth with a short delay based on from like when the X-ray flare happened. This doesn't just happen in one molecular cloud. This is happening in lots of molecular clouds around the galactic center. Oh, I'm out of time. I only have like 2 slides left though, so thank you. So this is what that looks like in a pretty picture. And so we can actually use this X-ray data towards, this is a paper from Sam Brunker and Danya Albaslani, where we did this towards 2 clouds, the Styx cloud and the Stone cloud. This is what that X-ray fluorescence looks like on there. So you have the X-ray flare come through and light up individual slices of the cloud. This is the actual data if you want. You have the molecular line data in the background grayscale and the X-ray years 2010, 2011, 2013, 2015, 2016, and 2017 as contours on top. You can see a remarkably good agreement. So we are actually lighting up the molecular gas with these X-ray flares. Then you can, super fun, build 3D models of these clouds. So talk to me about that if you're interested. But relevant to the 3D CMZ work, that means that if you can actually trace out all the different clouds that have X-ray flares, then you can actually work back when that X-ray flare happened if you know the 3D position of the cloud. So if you can simultaneously solve for the 3D position of the cloud using, for example, all of the other indicators that we have, then they can also give you a measure of when Sagittarius A star had flares, how many flares that it had, and it's something that you can put into your fitting routine to try to optimize as well. And we're also doing super cool new simulations with new physics and zoom-ins. So I will just leave that there while I take questions because I'm over time. Thank you.
Thank you. We have time for questions. Adam?
Sorry, really cool work. So it sounds like in the Milky Way, the turbulence in the CMZ is driven by the shear of these gas flows coming in or something, right? So connecting a little bit with these X-ray flares that you were just talking about, are there other terms in that turbulence analysis, that pressure, that maybe in a more generalized sense could be important for galaxies that maybe don't have, they have very similar CMZs, but without those inflows that are nicely feeding things?
Yeah, that would be, exactly, that would be really different. So barred spiral galaxies and non-barred spiral galaxies have different properties in their central regions for exactly this region. So if you don't have material being driven in, you're not only missing the inflow of material, you're missing the inflow of energy and turbulence, which just totally changes the star formation and seems to make it much more dynamic. Yeah.
Thanks.
Yeah, great review. Do you have an estimate for the gas inflow rate onto the supermassive black hole? You talked about the inflow rate onto the CMZ, but do we have any quantified number of how much is getting in closer to Sag A star?
Yeah, not that I'm aware of. I think that's what we're trying to figure out. If somebody has one, talk to me, but I'm not aware of any. Yeah.
Because there's numbers for the outflow rate, what gets kicked out. So just wondering how it connects with what's coming in.
Yeah, good question. I'm also curious. Yes.
Just one last question.
So I was wondering about the tilts of the structures in the CMZ. I mean, I've learned that there was one thing tilted at 28 degrees, but it looks like there's multiple tilts of different structures in there. What is it and what explains the tilts?
Yeah, so the preliminary model that I showed, that was just like top-down views, and those are really right now, we're not even looking at the Z structure. Of course, there's tilts in the Z structure as well, but those are just tilts in like the top-down of those X2 orbits. Yeah, so I don't know if that answers your question, but there should be like, there's definitely tilt in the Z direction because like we see like an oscillation, right? So it's probably like an ellipse orbit that has like a vertical oscillation, but then maybe is like kind of crooked and then maybe, yeah. I mean, if you look at the simulations, I feel like it's really easy to see how do you just draw an ellipse on top of that? And so like you don't expect the data to be a perfect fit, but I can't say anything about like the tilt yet.
No clear plane of symmetry, basically.
Yeah. Yep.
Okay, let's thank Kara again. Our next speaker is Rebecca Levy, presenting on young massive star clusters and feedback in NGC 253.
Yep, it's on. Okay, awesome. Thank you so much, everyone, for coming to this talk and for the organizers for giving me the opportunity to speak with you today. I'm also really excited that I am going right after Kara, who has done a fantastic job introducing a whole bunch of things that I'm going to talk about in another Galaxies CMZ. So I'm Rebecca Levy. I'm a postdoctoral fellow here at Space Telescope. And I'm going to be talking about one specific galaxy today, a starburst galaxy called NGC 253. And in particular, I'm going to be focusing on this very, very, very central region in this little blue box in the zoom in, and the very center of this galaxy. So a lot of the work that I'm going to be talking about today is specifically some of our new JWST results. I am by no means the only person working on this. We have a large team of more than 50 people across the globe who are working on this, many of whom are in the room. And so I really want to shout all of them out, especially the people who did the data reduction, which has been interesting. Okay, so Kara sort of already introduced us to star formation in extreme conditions, so I'm going to go through this a little bit quickly. So in the past universe, we know that the cosmic rate of star formation was higher. We know that the density of molecular gas in the past was higher. And so you might just think, okay, more gas, more stars, we're done. That's it. It turns out it's not quite that simple, unfortunately. Galaxies in the past don't look like galaxies today. They're smaller, they're clumpier, they're more turbulent, they're more compact. And so all of that, the fact that there's higher gas densities in general, they're more clumpy, they're